Hey, this is chapter 30, and up to this point, actually, we discussed some different types of manufacturing operations, and we discussed some machining, some forming, forging, casting operations, and they were all actually for producing parts. But this time, from this point on, we have three chapters remaining, and these are all about joining these parts. And we have different ways to do it. We have mechanical ways, and we have some welding type of processes. This is the first chapter about it, is fusion welding process, and in the next chapter we'll be discussing solid state welding processes, and the last one we'll be mostly discussing some mechanical types of actually joining the parts. And in this first type of welding process, we need to have actually some amount of heat generated by different means, and then with the help of this heat, actually, we melt some interfaces of parts which are going to be welded together, joined together, and then by using some different means, we try to join them. And in this process, since it's called as actually fusion welding processes, we need to be having a kind of doing coalescing of materials so that the strength of the joint is better. And for that purpose, we need to actually melt the materials at the interface. Two regions, two parts actually should be melted so that they will be joined in a firm manner, and you have actually stronger bonds between the parts. And in some cases, you may need to use extra material so that the gap between the neighboring parts is actually filled with these compatible metals. And if you don't want to use actually filler metal, that might be possible, but the thing is that the gap between your metals, between your parts should be very low. And in such cases, these processes are also called as autogeneous type of welds. And the first type of fusion welding process we are going to discuss is oxy-fuel gas welding. And as you see in this term, we have fuels and we have oxygen. That means we will have a kind of a combustion between oxygen and some types of fuel. And with the help of this combustion, actually, we will be generating heat, and this heat will be increasing the temperature of two parts, and then by maybe extra filler metal or by pressure, we will be joining these parts. And for most of the time, as the fuel, we use acetylene. And if that is the case, we call this process oxyacetylene gas welding. As you see, it's abbreviated as OAW. And, and this actually welding process, what we do, we actually burn this acetylene gas. As you see, this is a reaction. We have acetylene here. We supply some oxygen, and then we have the primary reaction. This is the first stage of combustion. And as you see with this one, we generate carbon monoxide, some hydrogen, and some heat. And this is actually not much. This is actually 1/3 of the overall heat we are generating in this oxy-fuel type of welding process. And after this primary reaction, we have a secondary reaction, and the secondary one, this time we are burning carbon monoxide and hydrogen. Obviously, again with the oxygen. And as you see at the end of it, we have carbon dioxide generated and some amount of vapor. But the thing is that the heat generated in this stage is higher than the heat generated in the first stage. It's actually corresponding to the 2/3 of the overall heat we are generating in this process. And you can see the typical, actually, let me show you another figure here. Yeah. This is a typical arrangement we are using in such kind of oxy-fuel kind of welding processes. We have a tube for oxygen. We have a tube for fuel we are using. And these are actually mixed at the torch, at the tip of this torch. This is called this welding torch. You can see the details of this welding torch. Oxygen is coming from here. We have the acetylene here coming here. And we have this mixing chamber, and inside here, we have the combustion, and at the tip of it, we will have flames. And you can see the type of flames here. Depending on the actually ratio of oxygen and your fuel, you may have a neutral flame if the ratio is 1:1. But if you have more oxygen and less fuel, then it's called as oxidizing flame. and you cannot obviously use it for all the metals. You may only use it for mostly some copper type of metals, since once you use it, obviously you have oxidation, and in some metals that might be protecting your welding zone in a better way. So that might be the case where you need to use oxidizing flame, but it's less commonly utilized. And then if you have more fuel and less oxygen, that is called as carburizing. And there are also special applications where you can use them, but for most of the time, we prefer to go with neutral flame. And you can see a close-up view of this welding, oxyfuel welding. This is our welding torch. It has a supply from here, and we have flames. And with the help of these flames, the base metal is actually melted on this around this region. And if you bring another metal which is to be welded, then if you have a gap, obviously you need to fill this gap with the help of filler rods. And you can see that after this torch is actually removed, this part will be solidified and weld will be actually completed. And now I will talk about some other types of this actually type of welding. And you may use again the same type of torch, but this time instead of using some filler method, what we do, we heat two surfaces, two interfaces, and then this is actually the pressure gas welding. You see with the same torch, the surface and surface of the parts are heated, they are melted, and then with the help of pressure, they are joined together. And we need to be actually applying this force maybe for until they are solidified. But the problem is that you see we have excess material. If it's not a problem for you, then that is fine. But if this surface is going to be used in some assemblies, then you need to do some further, let's say, machining operations. And the type of actually filler metals are highly important in most of the welding operations. As we discussed, if the gap is very low, then you don't need to use filler metal. But if the gap is larger, then you need to apply some extra metals inside so that once welding is over, we have proper connection between the parts. And they may be in the form of rods or in the form of continuous wires. Another difference is that some of them may be just bare, they have nothing around it, but most of them have usually are coated with flux. It's a special material. Inside this flux, we have different chemicals, and the function of the flux is actually to, not to have any oxidation during the process, and it will generate probably a gaseous shield around your zone so that the quality of the weld will be better, and any actually unwanted substances will be removed from the zone with the help of this flux. But the thing is that if you are using flux, and that means some amount of slack will be developed. Actually, slack is not shown here, but we will see in other type of welding operations that we have a little coating around the welding zone that is called a slag, and that should be removed once actually your weld is solidified, once the temperature is actually decreased. And again, the slag is higher useful while your welding is actually cooling down. It again protects it from oxidation, and that is actually a nice feature of flux and slag. So you go with flux, which is the coating around your filler metal, and once you do the welding, once this actually filler metal is melted, and that will be solidified obviously around the welding zone, and that is going to turn into slag. And once everything is over, you need to remove it by doing some maybe wire brushing or by some trimming or by applying some impact forces. You can easily remove slag. And we have a table here, as in the case of other chapters. It's actually a nice summary of the process we are going to discuss in this chapter. And we'll be discussing all these welding operations. It's stated whether they are performed, they are done manually or in an automated manner, their principal advantages, whether they are quite difficult or easy to do, and some other types of issues about current types, if they are using arc type of heat supply, whether we are going to have any distortion on the resulting surfaces, and their typical cause. So once this chapter is over, again, if you want to compare all these different welding processes, that table is actually a nice one. And I have another process called thermal welding, and this process is a special one. That is a combination of actually welding and casting processes. So how is that? Let me show you a sketch. But before that, in this welding process, we make use of some powders, metal powders with some metal oxide. So we mix them together, and then what we do, we put them inside this kind of tank hopper, and then we do ignition. And with the help of chemical reactions, these powders, the virgin metal powder is actually melted. We have high temperatures, and this molten metal is actually poured into this basin. And then with the help of the gate and kind of screw, this molten metal is transferred to the actually welding zone. And in this example, actually, we are trying to weld some 2 railroad rails. So we have 2 parts. Only this one part is shown here. But as you see, this molten metal will be going through all the surface of your rail, and we have another one beside. So with the help of it, these rails are joined together. It's a very compact way of doing it. It's flexible. You can easily transfer your system from one station to another station and do the welding. And in this, the most common type of actually powders are aluminum and iron oxide. And that is actually much easier to do with them. So that's why they are highly utilized. And during this process, obviously we need to melt iron, and that's why actually temperatures are increased to very high levels. But the process itself is not that complicated. And we may even actually use this process not for joining, but we may even do it for repairing some parts. So for instance, if one part of this rail, let's say this corner, is broken, then you may arrange your mold accordingly and try to cast that part. And that was actually the first type of welding processes, first type of fusion welding processes, oxide field type of welding. And now we will start another type of fusion welding process. It's called as arc welding processes and non-consumable electrode, which means that we have an electrode which is responsible for arc generation, and that is mostly tungsten. And in the next section, we will see that there are also arc welding processes where we consume the electrode. But in this one, that is not consumed. We can have a typical actually welding equipment and welding torch again. This time, as you see, we have an electric supply. It might be AC or DC, and that is must in this arc welding process since the heat is actually generated with the help of electrical energy. We have arcs generated, and obviously for that purpose, we need to have a power supply that might be an alternating current type or direct current type. And with the help of them, little arcs generated, and these arcs actually increase the temperature of the metals maybe up to 30,000 degrees. And as I mentioned, in this non-consumable type, we are using tungsten as the electrode. And you can see in this torch that at the center, we have the tungsten electrode. But again, if the gap between the parts is a bit larger, then we need to use filler wires, filler metals, and they should be compatible with the parts actually, which is going to be joined together. Another important thing about this welding process is that we need to be supplying some shielding gas through this torch so that we are not going to have again an oxidation inside our weld or around our weld. And as you see, that's why actually in this equipment we need to have an inert gas supply. And this is not obviously, we are not doing any combustion, but it's only for obtaining an inert atmosphere around our welding zone. And we have another extra thing here you see is cooling water supply. Since the temperature of this torch is quite high, we supply this water so that the temperature of the torch is around acceptable levels, and it can be used manually and the welding can be done. In terms of actually currents, we can use direct current or alternating currents. And in the direct current, actually, the polarity is highly important. And depending on the polarity, you may be welding some thinner and deeper ones, or some larger but shallow ones. So it depends on the polarity a lot. So let's have a look at two types. The first one is straight polarity, and it's also called as direct current electronegative type of welding. As the name implies, the negative side is actually electrode, so it is a cathode, and the workpiece, which is going to be welded, is the anode. And in this one, actually, we can easily weld some narrow and deeper welds. This is actually shown here. As you see, it's going deeper a lot, but the thickness is not that much. But on the other hand, if you follow reverse polarity, then we need to have electrode as the positive side and the workpiece as a negative side. And if that is the case, then we can have very actually thin but actually quite wide welds, and this is mostly utilized for obviously sheet metals. And if you don't want to actually harm the remaining part of your sheet metal and just join these sheet metals from top surface, then you should choose actually reverse polarity. And for the AC type of actually power supply or current method, we have arcs actually pulsating at very high frequencies, and that is mostly used for some thicker workpieces. And for thinner and for intermediate thicknesses, we go with direct currents. But for the thicker ones, it's better we use AC. And another thing is that since the gaps are quite larger in this case, we need to be using some larger diameter electrodes. And let's have a look at some types of this non-consumable arc welding processes. The first one is obviously the gas tungsten arc welding. As the name implies, we are using tungsten as electrode. And in the earlier days, it was called simply as tungsten inert gas. But these days, we prefer to use the term gas tungsten arc welding. And in order to fill these gaps between the parts, we are using filler wire. And with the help of actually, we try to obtain a kind of actually constant gap between the electrode and the workpiece. This distance is highly important. If this is satisfied, then that means we are going to have arcs in a stable manner, and the quality of our weld will be much better. Another issue about the filler methods is that obviously they should have similar properties with respect to the metals which are going to be joined, and we are not using flux as in the case of oxyfuel welding or another arc type of welding we are going to discuss. Flux is not utilized, so at the end of the process, we are not generating any actually slag. Slag is not generated in this tungsten inert gas type of welding. And we may also do this process without using any filler methods, obviously, but as I mentioned many times, the gap between these parts should be very low. If the gap is larger, then for sure you need to use filler method. And with this process, we can join various types of products, various types of metals together. And for most of the time, we use it for actually thin metals, and we use obviously reverse polarity and DC power supply, current supply. But the problem is that we haven't seen shielded metal arc welding, but its cost is a bit higher than shielded metal arc welding. But the advantage is that its welding quality, the surface quality is a bit better compared to that popular process, shielded metal arc welding. And instead of using actually this tungsten, we may use plasma. Plasma arcs may be utilized, and if that is the case, then the process is called plasma arc welding. And you see again, the temperatures are quite high, and we know that plasma is simply actually ionized hot gas. And inside this hot gas, we have equal number of electrons and ions. And with the help of it, actually, we can easily join some thicker workpieces. This is actually the best advantage of plasma arc welding. We have two types of plasma arc welding: transfer arc and non-transfer methods. In the transfer arc method, the thing is that the part, actually the workpiece, which is going to be welded with another workpiece is the part of our electronic circuit. It's a part of that circuit. So arcs are generated actually in between the torch and the workpiece. But in the non-transfer method, the workpiece is not in the electrical circuit. The arc actually is generated between the electrode and the nozzle itself. And then later, the heat generated in between is transferred to the workpiece with the help of plasma gases. Now you can see the difference here. The first one is transferred, as you see. The workpiece is part of the circuit. The arcs are in between this electrode and the workpiece. But in the non-transferred gas, the arcs are generated in between this nozzle and the electrode. And then later, with the help of this gas, heat is transferred to the workpiece, and then later they are joined together. But in the first one, the arc is obviously in between the electrode and the workpiece, so we don't need to have a proper transfer. We again, as in the case of tungsten inert gas welding, we need to use shielding gas around so that oxidation is actually eliminated. And in this process, actually, the quality of arc is a bit better. We have much stable arcs. We have less thermal distortion, and the energy is concentrated on the little point. So that's why actually we can easily weld parts having high thicknesses, and even they have some thin, let's say, gaps between them. That is mostly utilized in such cases.